So we'll have a look now at the additive manufacturing process known as material extrusion. This is, without a doubt, the most popular 3D printing process. It's also the one that is most readily understood. It's the process that if you have a home 3D printer, this is what the 3D printer, this is the process that the 3D printer uses. Before we do that, though, let's take a step back and try to understand the additive manufacturing standardization process. So recently, dating back to 2009 and before that time, there's been a push to standardize much of the technology and processes associated with additive manufacturing and 3D printing. So in 2009, the ASTM established the International Technical Committee, known as F42, on the additive manufacturing technologies. All right. 2 years later, ASTM and the ISO began jointly to develop a additive manufacturing standard. So ASTM is a standards organization based in the United States. ISO is a European standards organization. So when these two organizations get together, they're kind of sort of developing a worldwide standard. Okay, so that's what was going on in 2011. ASTM, as I already mentioned, formed Committee for F42 for Additive Manufacturing Technologies. The ISO formed a similar committee known as Technical Committee 261 on additive manufacturing. And they decided that they were going to develop standards that would be co-branded ISO/ASTM, so that they were going to jointly be developing these world standards for additive manufacturing. In addition to that, ASTM is also developing standards for the National Center for Defense Manufacturing and Machining, which of course, has to do with standards involving the U.S. military. All right, so the F42 subcommittees, right? So F42 is a committee dealing with additive manufacturing technologies. There are subcommittees under F42 that are in charge of different aspects of additive manufacturing. In fact, there are 8 subcommittees under the jurisdiction of the ASTM F42 committee, and these are test methods, design, materials and processes, environment, health and safety, executive committee, terminology committee, strategic planning committee, and then the committee that is jointly going to be kind of communicating and liaising with the ISO Technical Committee 261. Okay. And you can see the designations for each one of these subcommittees. They all have the F42 prefix and then .01, .04, so on and so forth. So let's talk about some of the standards that they developed. All right. These are not all of these standards. There's been new standards that have come out that I haven't included in this, but what I'm trying to do is just hit the really important ones here. So they developed test methods. The F42.01 developed some test methods for testing the additive manufacturing materials and parts and processes. Okay. The design subcommittee developed the AMF file format, which we've already talked about in one of the earlier lectures. So they're responsible for that, and also standardizing that file format for 3D printing. We have a number of standards under the materials and processes subcommittee. Many of these deal with metal 3D printing, metal additive manufacturing, because that really is one of the processes that is most readily applicable to manufacturing and the technologies and products that are that are developed for consumer use. And then finally, we have the F42.04 design subcommittee developing additive manufacturing general principles and terminology, something that we will use in this class. Okay, so there are a couple of standards that we're going to use in this class specifically, and the first one is the process classifications. Okay, this is from the ISO ASTM 52900 2015 additive manufacturing standards, which is the one that set out the 7 basic processes that we use to define and categorize additive manufacturing. Okay, so we have liquid-based processes, and these include vat photopolymerization, material jetting, and material extrusion. Then we have solid-based processes, which include sheet lamination, directed energy deposition, and that's wire-based directed energy deposition. And then under the powder-based technologies, we have binder jetting, powder bed fusion, and then the other directed energy process, directed energy deposition using a powder system. All right, so these are the standard 7 processes. There's all of the 3D printing and additive manufacturing, all the various different types of 3D printers and whatever will fall under one of these categories. Okay, basically they'll either be liquid-based, solid-based, or powder-based, and then it'll be closely aligned to one of these other technologies. The one we're going to look at today with this lecture right now is material extrusion. All right, so let's get into it. Material extrusion, the figure shown in the right is a basic process for material extrusion. All right, and basically what's going to be going on is the material here, which is going to be on a spool, is going to be fed into a housing here, the extrusion head, where this plastic filament is going to be melted and then deposited layer by layer to build up the part. All right. The official definition for material extrusion, and again, this is the standard definition, is an additive manufacturing process in which material is selectively dispensed through a nozzle or orifice. Okay. Typically, the build material is going to be a thermoplastic, right? Now, note that we're not talking about a thermoset here. Remember that there's 2 types of plastics, thermoset and thermoplastic. Thermosets are typically found in vat photopolymerization processes. Thermoplastics are typically used in material extrusion. We'll talk about why in a few slides, but we can also have ceramic for a build material. We can have food for a build material. The material distribution method is an extrusion process. Now, what an extrusion process means is basically we're going to take, in this case, we're going to take the plastic filament, the plastic, and which is a solid, which starts as a solid, and we're going to melt it, and we're going to deposit it when it's in a liquid state. And then that melted plastic is going to re-solidify rather quickly so that we can build layer by layer on top of that. So that's the extrusion process that we're going to be using to build our parts with the material extrusion technology. And then the binding technique for this is heat and chemical binding. Okay, the binding in your typical 3D printer, in your typical material extrusion 3D printer, is just the heat from one layer to the next layer. Okay, so they're kind of welding together or gluing together. Maybe a better term would be melting together. Although we want to control the amount of melting, obviously, because we want it to maintain its shape. So we can't have complete liquefaction of it, so it can still maintain its structural integrity. All right. So let's talk about the different steps in a typical material extrusion process. So a typical material extrusion process is going to follow these three basic steps. The first step is the first layer is built as the nozzle deposits material where required, according to the layer, the cross-sectional dimensions of the layer, where required, onto the cross-sectional area of the first object slice. Okay. At this point, the platform here, you can see the build platform, is going to be basically as close to the heated nozzles here as it can be. So it's going to deposit just that first layer. Then after the first layer is deposited, this build platform is going to move down one step, or the head can move up. Depends on the 3D printer how that's going to work. But let's say that the build platform is going to move down. It's going to move down equal to one layer thickness, and then the next layer is going to be deposited on top of that. Okay. Third, the layers are fused together upon deposition as the material is in its melted state. Okay. So the material is going to extrude in a liquid state, but it's going to solidify rather quickly. And it's basically, it has to solidify, not necessarily 100%, but it has to solidify enough by the time the first layer is done so that the second layer can be deposited on top of it and not, as I said, and maintain its structural integrity, maintain its geometric profile and shape for the different layers. Okay. So that's the basic outline of the material extrusion process. Some noteworthy material extrusion technologies. Okay. First of all, the big one is FDM, fused deposition modeling, and that was developed by Stratasys. Remember, that was one of the first machines that was commercialized right after Charles Hull. This was developed by Scott and Lisa Crump. Now, it should be noteworthy that the FDM process, the fused deposition modeling, that term is copyrighted, right? And so that's why that term is usually only associated with Stratasys. But like Kleenex and Xerox and other kind of technologies that came out and became such a predominant power in the industry that we just refer to things as, Kleenex when we actually mean tissue. And we refer to things as a Xerox machine when really it's just a paper copier. FDM, or fused deposition modeling, became the go-to phrase for plastic 3D printing using the material extrusion process. Okay, so technically speaking, we shouldn't be calling all of the machines FDM machines. Another good term to use would be FFF, fused filament fabrication. You can see it down here. That is not a copyrighted term, so that one's free to use. 3D Systems came out with a competing technology called plastic jet printing, which basically it's a material extrusion process. But again, they had to name it differently because, and actually they also have to change the technology slightly so that they're not going to be infringing on patents held by Stratasys. Okay, so as I said, some other names for material extrusion process are fused filament fabrication or contour crafting. Contour crafting is more associated with large structural 3D printing. Okay, there's other technologies and terms as well. I think in one of the earlier lectures, I mentioned BAM, BAAM, which is big area additive manufacturing. That is a material extrusion process. BAM is a copyrighted phrase or term for that. All right, so let's talk about some of the strengths and weaknesses then of the material extrusion process. So some of the strengths is that it needs no post-curing. All right, so after you're done with the print, once you remove it from the build platform, it's done. Right, it is structurally sound. It's ready to be used. However, you're going to be using it. So there's no post-curing like in the powder bed fusion processes, where oftentimes we have to sinter or do some kind of heat treating, or in the case of that photopolymerization, where we might have to do some UV curing, light curing. It has production grade strength, although the strength is not super good. Okay, it's not going to have the strength of obviously a metal part, but it is a good plastic strength. I would also say that the strength in a material extrusion printed part is oftentimes going to be stronger in some directions and weaker in some other directions. And we'll talk about that in some later slides. There is really a wide range of materials. There's a lot of materials. You can build parts in ABS, which is a very strong plastic, flexible plastics. They now have materials with carbon fiber chips in the filament, so you have that added strength. They have TPU, PETG, PLA, nylon, all kinds of materials that we can use for different material properties, different purposes. So it's really fantastic, the amount of materials that we can print with. There's a minimal amount of waste, right? Realize that we're only going to be using the material that we need in the print, right? With the exception of some of the supports, which is not a whole lot of material anyway, but any support structure is going to be the only waste that you would have in that. And then we can build with large build volumes. Like I mentioned, the BAM, BAAM, Big Area Additive Manufacturing, is a large volume, large scale 3D printer using the material extrusion process. Contour crafting can build homes and other structures, so it is very large scale. Some of the weaknesses that we have in this, first and foremost, the surface finish is not very great. If you've ever held a 3D print done with a material extrusion process, you'll notice that you can see the layers. Oftentimes you can run your finger over it and you can feel the layers with your fingernail, or just with your finger in general. So the surface finish is not very good. Surface finish on the top and bottom, is going to be better generally than the surface finish on the sides, which is where you have the layering. But still, even on the top and bottom, it's not going to be, really that good. And if you want good surface finish, you are going to have to do some post-processing and finishing of your part with different techniques and to kind of smooth it out. It has a limited accuracy. The accuracy is good, right? But it's not great. It's not on the level certainly of the vat photopolymerization. Some of the material jetting processes have very high resolution. So it's not good, but it's not terrible. It has a relatively slow build time, right? So it could take hours to build a part and not really a very big part. So it is rather slow. And it does have relatively unpredictable shrinkage. So parts, because we're talking about a material that's going to be extruded in its liquid form and then it's going to dry on the bed while you're adding layers to it, that drying process is going to have an inevitable shrinkage to it. So you are going to have some contraction of the plastic, which is going to affect dimensional integrity. It's not great. There's not a whole lot of shrinkage going on, but depending on the accuracy level that's needed, it might impact whether you decide to use it or not. All right, so what is the short history on material extrusion? Well, as we heard earlier, in 1989, a patent was filed by Scott Crump. for the FDM process. Stratasys was founded that year by Scott and his wife Lisa Crump. In 1991, the first commercial FDM printer or machine was developed by Stratasys, and it was commercialized or sold. A year later, the patent was issued for FDM to Stratasys. Okay. Now, and this is really important. In 2009, the FDM patent expired. Okay. And what that means was that in 2009, all the other companies that were waiting to get into the 3D printing market but could not, because Stratasys held the patent for this process in 2009, that's when the industry exploded, really, with 3D printers, and especially home 3D printers. And that was the time when the RepRap Mendel came out and MakerBot came out. So really, we could mark 2009 as the year that 3D printing really exploded into the commercial scene for the first time. Okay. All right. So let's look at the material extrusion materials. Right. The materials are one of the real strengths, real pluses of this 3D printing process. In the material extrusion process, a plastic in solid form is heated to a semi-liquid state, right? So it's not liquid. It's kind of it's kind of like molasses, or a good analogy to this is, like a hot glue gun. Okay. So it's in a semi-liquid state and it's extruded through the nozzle onto the build plate. The extruded material relies on cooling only to solidify the semi-liquid material. Okay. So the build and support material, and this is not an exhaustive list. Okay. These are just some of the big ones, but thermoplastics, that's the build and support material. A thermoplastic, as we'll talk about, is a plastic that can be melted and reformed over and over again with minimal degradation, as opposed to a thermoset where if you melt the thermoset, it will basically burn and it can't be reformed again. So noteworthy thermoplastics include ABS, PC, polycarbonate, PPSF and PPSU, polypropylene, PEI, which is known by the trademark Ultem, and then PA. There's other ones as well. There's PLA, there's nylon. I can go on, and we'll talk about that in a couple of slides. New systems are being developed which use ceramics, right? Which use food, so we can 3D print our food. Yum. Biocompatible materials, that is materials that can be used in and on your body, and glass as well. Now, one addition that I would make to this is also we have new systems which are kind of revolutionizing the material extrusion process, which print with metal. Okay, so we can actually have metal 3D printing in the material extrusion process, and we'll talk about that later. So this leads us to the discussion of thermoplastics, right? So a thermoplastic is a polymer that changes to a liquid upon the application of heat and solidifies to a solid when cooled. All right. It's remoldable. It has superior finishes. All of these examples are thermoplastics, made of thermoplastics. It can be chemically resistant. It's rigid or flexible. And it basically has three classes: ABS, polycarbonate, and high performance. Okay. So when we talk about the classification of thermoplastics, we can use this thermoplastics material pyramid. Okay. So down at the bottom, we have the most basic plastics. These are not the good engineering plastics. Those are at the top of the pyramid. All right. So these are just kind of your bargain basement, dollar store kind of plastics. Above that, really, you have your standard plastics. Okay. And as the name says, these are for non-critical applications, right? Toys, things like that. So this includes ABS, PVC, polyvinyl chloride, polypropylene, high density polyethylene. All right. So again, these are non-critical applications, standard plastics. Moving up the pyramid moves us up in its performance range. And so in the green layer, we have engineering plastics. These are going to be better structurally. They're going to be thermoformable. That means that they have good characteristics for melting and reforming. And they're also bondable, so we can glue them together. They're not going to degrade by the application of glue. So these include polycarbonate, acrylic, nylon, and acetyl. Right. Good chemical resistance, general purpose bearing, and wear. And then right at the tippy top, we have our advanced engineering plastics. These are steam resistant, thermoformable, transparent, translucent, high temperature, superior chemical resistance, good wear resistance. These include PEEK, PTFE, PSU, PEI. Some of these you might be familiar with. Some of them you probably haven't heard before. We'll get into what each one of those is in a couple of slides, so I'll hold off on that. But why does a thermoplastic behave in this manner? Well, in a polymer, we have long chains of hydrocarbons that are linked together. So in this figure on the right, on the left, we have a thermoplastic. This is a thermoplastic, and then we have a thermoset. You'll notice the difference between a thermoplastic and a thermoset. A thermoset has cross-linked members. So these black nodes right here are cross-linking, right? The thermoplastic does not. Thermoplastic is kind of like if you took a bunch of cooked spaghetti and just dropped it on the ground. Okay. The spaghetti is not going to cross-link. So each spaghetti noodle is not going to link to the other one. They're going to still stay separate. That is what the thermoplastic is. Thermoset, well, imagine those noodles that we dropped on the ground, and now each noodle, as it crosses another noodle, it's going to bond to that. So it's going to make this kind of, these cross-link or X-like shapes. Okay. And that's what gives us the different properties of thermoplastics and thermosets. Thermoplastic can be melted and reformed. Thermosets cannot. In addition to thermoplastics and thermosets, we have amorphous plastics and semicrystalline plastics. Amorphous means that they don't really have any kind of organized shape in the chains of hydrocarbons. Semicrystalline, we do have some kind of organized shape. The amorphous and semicrystalline has to do with the pyramid here. So the top of the pyramid is where you're going to find our semicrystalline materials, and the bottom of the pyramid, this is where you're going to find our amorphous materials. And now, as I said, the behavior of the thermoplastics works like this. When they're hardened, they're solid, we heat it, they soften, they cool, and we can continue this cycle. All right. So we can form it, bend it, do all kinds of things. With the thermoset, it's going to be permanently hard, right? So if we heat it, it's going to be softened, it cools, and then that's it. There's no more reheating that we can do to that. All right. Now, real briefly, I don't want to spend too much time on this because this is not a materials class or a class that's going to go into any detail in the thermoplastics. That would be an entirely different course, but I want to hit some of the big names in thermoplastics with respect to FDM and 3D printing of the material extrusion process. So, one of the main plastics is the ABS plastic, which is known as acrylonitrile butadiene styrene. Okay, that's a mouthful. It's a rigid, low-cost thermoplastic, easily machined and thermoformed. And there's a lot of variations within that, okay? Many of these that I have listed here are proprietary to the Stratasys 3D printers. So they might have different names for different 3D printers, but you can see you have translucent, you have biocompatible, that is, it can be associated with food, you can sterilize it, and even this one is electrostatic discharge resistant, so it's electrically inert. Then we have polycarbonates. These are transparent, tough thermoplastics with high impact strength, excellent chemical resistance and electrical properties, and good dimensional stability. So we have polycarbonate, right? As I just said. We also have a polycarbonate ABS kind of hybrid material and a polycarbonate ISO hybrid material. Some of the high performance materials include ASA, which is polyacrylic styrene acrylonitrile. These are tough for me to say. Polyphenol sulfone, right? PPSF and PPSU. Ultem 1010, Ultem 9085. Now notice Ultem 9085 is high heat and chemical resistance. So we're getting some really good plastics here. And then of course we have nylon, unparalleled toughness, superior strength and durability, very fatigue resistant. So these are good materials, good plastics. They're getting close to metal properties. They're not there yet. There is some distance between the plastics and the metal, but they're getting close to the metal properties in many of these applications. All right, so I think that is going to give us the first part of this lecture on material extrusion. In the second part of the lecture, we'll pick up with the 7 basic principles of the material extrusion process.